Good morning.
Morning, Doug.
Hannah and Connor are in the house.
Good morning.
Hannah's got her duck shirt on. Go Ducks. I was a duck. I guess I still am.
Same. I wasn't a duck. I'm just a duck fan.
So hey, Doug, about the homework, the 4.4 homework.
Yeah.
So for 20. Oh, sorry, what?
Yeah, go ahead.
Oh, for 28 and 32, those two problems they just wanted the y, right? With like all the constants like not figured out.
Yeah, don't figure it out.
Perfect. All right, that's what we did. Awesome.
Yes, and the problem we solved at the end of yesterday illustrates exactly why they don't want you to solve that. Because that is terrifying. But we did it.
First try too.
I can't believe it. It's a miracle.
I don't know if I'd call that first try.
Actually, I want to show you guys something about that was kind of fascinating. Since y'all are here on time, I'll show you, and everybody else cannot see it. Because when it didn't agree originally, my first thought was, let's just not figure it out, because it's literally going to take 2 hours to go find whatever stupid small thing that I did wrong. Oh, did I get rid of that? I think I need to get that back. I actually want to show this to you. Unfortunately, I got rid of the note, so I have to get it back really quick. Class notes. This will just take a second. Come on. Come on, let me go. Yeah, interesting assignment. There we go. Yesterday was July 28th. Oh, it was still in there. Still. I only showed this to you for your sort of mathematical curiosity, but I think it's kind of worth looking at. So that ridiculous matrix that 6x7 matrix that we got at the end of the day that I assumed was probably typed in wrong or something. Jeez, how much did we cover yesterday? I want you to stare at that matrix. Do you see any pattern there? Do you see any pattern to anything, or does it just look like numbers everywhere?
I mean, all the same numbers are popping up, like, tens and twos and fives, but I don't see a pattern.
So now start looking diagonally.
Yeah, there's a row diagonal. That's pretty cool. And zeros.
Like all of those were twos. And then this went 10, 5, 0, 10, 5. All zeros. 2, 0, 0, 2, 10, 10, 10, 10, 10, 10, 10, 10, except all negatives. This went -8, -4. This went 0, 8, 4, 0. Like, that's actually one of the things that made me realize, I don't think I did make a mistake to this point, because basically all of that pattern was accurate. The only thing, if you will, that was a little potentially weird is these were all positive 10s, whereas these were negative 10s. These were negative 8 4s, and this is a positive 8 4. But that's interesting. That's part of why linear algebra, Math 261, exists as a study, because there's some patterns to these things. You know, when the quote unquote real world produces the 6 equations, 6 unknowns, you tend to see patterns like this, and ultimately 261 exists exploiting those patterns, if you will, and how to kind of get it to work right. And the fact that those patterns exist is kind of why there's a matrix function in your calculator that will, you know, make this kind of thing possible, which is rather amazing, I think. Anyway, I thought you'd just find that interesting. Okay, so what must we look at today? As I mentioned yesterday, nothing new today. Your book titles this, I think, not very informatively, the superposition principle. I think I could come up with 4 or 5 names that I liked better than that, but let's see what's going on. And so let's say that we started out with y double prime minus 2y prime minus 3y, like we did yesterday and the day before, except for, like yesterday, let's put something on the other side. Well, let's keep it kind of simple. Let's make it 2t, but then this time, instead of like times e to the t, let's make it plus. And notice I'm going to try to make this work really fast. Notice I didn't say e to the 4t. I just said e to the t. That'll make the derivative taking a lot easier. So with the plus sign there, how do you think that's going to work? Would you agree from yesterday that our, if you will, our guess for this one would be y equals at plus b? That would be our guess for that. And then our guess for this one, if I call that y1 and I call this y2, our guess for this one would just be not just e to the t, but, you know, maybe c e to the t, some constant in front. Isn't that what we kind of saw yesterday? And again, it's very disappointing that we are actually guessing to get these 2 answers. And so what do we do with the plus sign? Are we really happy there's a plus sign there? Like, oh, good, it's a plus sign, not a multiplication sign. How does this work? So, you know, and then I'm sort of inclined to wonder, is this 2 different problems? Do I kind of do it once to get 2t and then do it a second time to get e to the t, or do I do it all at the same time? In other words, can I just say y is equal to a t plus b plus c e to the t and just like do it all at once? You follow my thinking there? Like, do you think that's a good idea? Do you think that will work?
No, because that's what you do when you multiply them together.
Well, yes, except there was a multiplication sign between them yesterday. That's what it was between them yesterday. So because there was a multiplication sign here, then there was a multiplication sign here. But today there's a plus sign in both places. And so should we do them separately, or can we even do them separately? And so you see the kind of the conundrum there. So I'm not really sure. I don't know, for the heck of it, let's go find one of them. Let's just go do like the y1. So if y1 is at plus b, then of course that makes y1 prime really easy. That's just a, and then of course y double prime is actually 0. So notice this is not going to produce the ridiculous 6x7 matrix that just happened a little while ago. So then if I plug everything back in, I get 0 for y double prime minus 2y prime, but y prime is only a, minus 3 times the function itself. So that'd be minus 3at minus 3b. And I need that all to come out to be 2t. That's if I just kind of ignore the ET for later, right? And so does this work? Well, notice there's only one t term there. So that means minus 3a has to become 2, otherwise this isn't going to work. And so we know a now has to be negative 2/3. And I just made this problem up, so that's why it didn't come out nicer than that. So is that still okay? Is it okay that a is negative 2/3? Well, notice the constants, negative 2a minus 3b. Since this is plus no constants, like that was just a 2t, it wasn't 2t plus 7. For that reason, then, these have to be nothing. And since we know a is negative 2/3, that makes this positive 4/3. And if I add 3b to the other side, then b is 4/9. So actually, that seems like it worked. So then we think we know what y1 is. So I don't know, let's just keep going. That was fun. So let's go get y2 then. So if everything, and again, this is going to go really fast because I chose really simple equations. And so if y2 is ce to the t, then the derivative of that, well, wait a second. No, that's right. Let's keep going on. So then the derivative of y2 prime is also just ce to the t, since the derivative of t is just 1. And that means the second derivative is also the same exact thing. And so we just have this big repeat. y2 prime, and y2 double prime are all the same exact expression. So that seems like that won't take that long then. So if I add all of those together, there's my y double prime minus 2 y primes, and then minus 3 y double primes. It's like an e. We don't want that to look like an e. You know, again, the question is, can we make that equal to just e to the t? Well, notice they all have an e to the t. So if I factor that out, I end up with c minus 2c minus 3c. So I guess that means minus 4c. Is that right? Minus 5c plus 1c. Minus 4c has to be 1 since the coefficient has got to be 1. So that means c is equal to negative 1/4. So we say, yeah, I guess I can get that to work as long as I pick c to be negative 1/4. So is that helpful, or is that a waste of time? Because that the problem wasn't those individually, it was them together. And to make sure that you see this, like, let's go back and, well, now let's find y. I think this will speak to you. In other words, this was our y where we kind of did it all together, right? So then I would say, okay, well, if that's true, then y prime is equal to the derivative of at is a, the derivative of b is gone, the derivative of ce to the t is ce to the t. And that would mean y double prime, the derivative of a, because it's a constant, is gone. And so there's all of our ingredients. And so we got to say y double prime. And then we move to minus 2y prime. So minus 2a minus 2c e to the t. And then finally minus 3 times y itself, which was at. So minus 3at minus 3b minus 3ce to the t. We need all of that to equal, well, what we said this was equal to, which was 2t plus e to the t, right? What do you notice about that? So is all of our work above this helpful or not helpful? Understand what I mean by that statement?
I say
Like,
it should still work. Yeah.
so there's an e to the t term, there's an e to the t term, there's an e to the t term. So it's those that are going to have to produce this e to the t, right? And then how am I going to get the 2t term? Well, you know, these are there's the only t term. And then, you know, I could sort of put a +0 here since these, if you will, are the constant terms. So does it make sense that, you know, that sort of in a sense gives rise to, you know, like 3 equations? In other words, c e to the t minus 2c e to the t minus 3c e to the t. That's going to have to produce the e to the t. And then we've got minus 3at that's going to have to produce the 2t. And then we've got minus 2a minus 3b that's going to have to produce the 0. Isn't that that's exactly what we did in the top, isn't it? So that work up above, we could actually have done these independently. Does that make sense? We could have done these as totally separate problems. We're going to get the exact same answer. Do you see that? And so, you know, in a sense, I could have done this either way, but the reality is kind of why, I guess you could say, I guess I could sort of say, hence y1 plus y2 is really just equal to y anyway. In other words, our final answer to this question is really just all of the stuff we calced all put together, -2/3 plus 4/9. And then it was minus 1/4. So that's actually our, well, again, notice it's actually particular. That's our particular answer. There's no constants in it. Now, that's not terribly surprising, maybe. We always, with derivatives and so forth, we always liked plus signs, right? Because then we could do them separately. And we, you know, if it's multiplication, we didn't like it because we had to do the product rule. So maybe that's not all that surprising. So they're linearly independent, I guess you might say, these answers. So good, we like plus signs. So as it turns out, you know, if I came back to this problem up here and, you know, I'm not going to do this, I'm going to erase this, but it's like if I came here and said plus sign, that's not that much more terrible. It just means I got to go do a y3 to find sign. So I'm not as troubled with plus signs as I am with minus signs. Do you agree with that? But here's the profound conclusion that produces the main topic for today, which is this. See if you understand the significance of this statement. So, couldn't this problem be thought of as 2t plus e to the t plus 0 then, if I wanted to? Why is that profound? To throw a plus 0 on the end of that? So this part of our solution sort of came from here, right? And this part of our solution came from here.
Are we saying that 0 is also a solution?
But isn't 0 a solution?
I mean, yeah, I mean, it makes sense because if y equals 0, then the first and second derivatives would also be 0.
So there's another constant on there.
Again, it seems, but what was when we first started solving second order linear differential equations, what type of equation did we solve? What was the name for that?
Oh, so if we have a 0, then we can solve it like and find a general solution.
Wasn't
doing
that,
it
didn't we
homogeneous.
find a whole solution for this when it was equal to 0? Wasn't this the homogeneous solution from chapter 4.2? Yes is the answer. Like that's actually part of the answer. That needs to be part of the answer. Like there's a +0 on the end of every one of these. Even if there's junk on the other side, there's still a +0 on the other side. And what we just observed is that with plus signs between them, they both end up answers. And so 0 is an answer too. So let's go consider the homogeneous solution to this. Well, doesn't this give rise to the auxiliary equation, which happens to factor to r minus 3, r plus 1, which means that r could be 3 or r could be -1. And didn't we say that when this thing was homogeneous, we said the answer to this, I'll call it y3, was, I guess I'll use the letter D, DE to the RT, like, and there's the two R's we just found. Isn't that what we said the answers look like? So that means we have kind of a y3 equal to, and I used C1 and C2 before, so I guess I'll keep using that. C1e to the 3t plus C2e to the -t. That's part of the answer too. Now, does it mean we've been wrong all this time? No. It just means we weren't making the answer as general as it could have been. Now, we did get lucky with something. Remember the curveballs, the I before E exception. Did we run into that problem here? Well, notice what was on the other side. What was on the other side of this original equation when we started was an e to the t, which means we kind of had an r value of 1 there. And did that turn out to be one of the roots of the auxiliary equation? The answer is no. You know, r was 3 and r was 1, sorry, -1. So it was not a match. Had this been r equals 1, that would have caused us some trouble. Do you understand that? Like our guesses would not have worked. So I want to say we got lucky, except for, you know, I was thinking about that, made sure it didn't happen, but.
So now do we just tack on the 0?
That's exactly what we do. So if you will, then the actual final complete solution is what we said before, y equals -2/3 t plus 4/9 minus 1/4 e to the t, but it also has these, it also has the homogeneous solution hooked onto it as well. And of course, there'd be no reason, you know, I used A, B, C. I could have went on to use D and E for those two constants. I was just kind of going back to what we said before.
So does that mean like every equation that we solved yesterday and our homework, like all that stuff needs to be in this form from now on? Like we need to solve the, okay.
Correct.
And then when we get the YP, when we get the particular answer, do we need to solve for the C1 and C2 as well? Like,
yeah.
Okay.
And so, and again, that's going to be tedious. Like we're probably not even going to do it. But in other words, if I came back and said, now y of 0 is 3 and y prime of 0 is 8. And so let's go solve for C1 and C2 and get a particular solution. We could absolutely do that. But it's just, you know, the answers to these are so big and ugly that's what's going on. So again, I ask you the question, was this wrong? Was that answer actually wrong this whole time? The answer is no. If C1 and C2 were equal to 0, then isn't that an answer? That's not wrong, it was correct. But it was actually just a particular solution. You didn't notice it at the time, but it was a particular solution where C1 and C2 were 0. So this was actually a particular solution, whereas now we actually have a general solution. Now, just for the fun of it, let's go. And I really want this to go into you for the test, but I kind of did this quickly going out the door yesterday. But I just want to make sure you can really do this, because as you know, we've illustrated, there's a lot of ways that you can make mistakes with this. And it doesn't take that long to check if you do this. And so let's check this. Let's see. So how would we check this? I got to share a screen. So I am saying that I think the answer to this is f of x equals, actually I'll use t since I was using t before anyway, and we said yesterday we can get away with that as long as you say f of t. We said the answers to this were -2/3 t plus 4/9. Said, yeah, and you keep going, and it was -1/4 e raised to the t power. And so there's our solution. We think that's the answer to our question. Right now, that didn't really help me check it. But notice again, what's cool about this is, in a sense, for the first time in our math career, we're seeing combinations of equations. Notice this is really a line plus an exponential. It's like two equations. We know what lines look like. We know what exponentials look like. We don't know what lines plus exponentials look like. No wonder we weren't able to kind of find these. But how am I going to check that? Like, that doesn't check it. I just graphed it. It's like anything could have appeared. I didn't check it. What did I do yesterday to check this? Well, what did our original equation say?
You did like f double prime. I forgot the original equation.
Yeah.
F
If
double
I take
prime
f
to f prime.
double prime, and notice that's prime prime, not quotes. You can't get both of them at once by hitting shift. And if you're looking at your screen, that's like prime prime. It's amazing that Desmos actually does this. So I think I can do this with t. So f double prime minus f minus 2 f prime of t minus 3 no prime. So just f of t. That all typed in right. Let's see. Well, like, what is that? Notice it wants t to be a slider. But if I go back in here and I say y equals that.
Wow, I didn't know Desmos could do that.
Yeah, isn't that cool?
That's really cool.
So, and then didn't we say that equation, that graph right there, f double prime t minus 2f prime of t minus 3f of t, in the original, wasn't that supposed to be equal to 2t plus e to the t? Now the test is about to happen. Y equals 2t plus e raised to the t. Is this good news?
Yep.
On, off, on, off. Yeah, it's good news, because what do we see? It's the exact same graph. It means we didn't get it wrong. Notice f double prime of t minus 2f prime of t. Where is it getting that stuff? Well, from this up here. Notice that graph actually wasn't, that's the actual picture of the answer. But that's actually not what I'm looking for. I needed to check to see if I took the second derivative of that and the first derivative of that and plugged it all into this, would I really get this? Now we can do that by hand, right? That's not terrible. I can take the first and second derivative of this, plug it all in here and simplify it and show that that's actually equal to 2t e plus e to the t. But isn't this kind of a nifty way to check it? And so it's interesting that that actually, although that's actually the graph of our answer, that wasn't checking to see if we got this right. Now, here's the interesting thing though. What we're saying is you could actually go on here and instead of C1 and C2, I'm going to put A. But we went on to say that the the better answer to this actually is this. C1e raised 2, and I want to know if you can guess what's going to happen here. 3 to the t. And then plus C2, I'm going to use B, e to the negative t. What's going to happen when I do this? Is this the same graph it was before? Well, notice the actual solution, let me turn these off. The actual solution to this thing now slides all over the place, right? Because of the C's, because of those constants, it slides everywhere. And by the way, what if I said, let's just play with this for a second. What if I said the initial condition is 0, 2? Do you agree that I just slid it so that it goes through 0, 2? So it's kind of like I just guessed the value for A and B. Is that the only way I can get it to go through 0, 2? Notice, no, there's actually thousands of ways you can get it to go through 0, 2. Do you see that? So notice it's kind of parabola-like right now. But what if I slide it over here? Can I still get it to go through 0, 2? Yep. Notice there's all kinds of curves that go through 0, 2. That's why just saying y of 0 equals 2 is not enough. You have to also come back and say you need the slope to be correct. Notice in the graph I just drew, the slope looks to be really steep, like say 10. So that's like saying y of 0 is 2 and y prime of 0 is 10. But if I slid it over to here and still made it go through 0, 2, notice now the slope is much lower, like maybe 3. So y of 0 equals 2, y prime of 0 equals 3. So there's only one graph that actually has the correct original starting point and the correct slope, but there's thousands of graphs that have the same slope. I'm sorry, that have the same original starting point. But here's the ridiculous thing. I just added all this stuff to the graph, and yet isn't this the exact same graph we had before? How come that is? How come it like changed nothing? Why did it change nothing? I just added all this stuff to it, and yet down here it's like it made no difference. Well, remember what that stuff was equal to? When you took this stuff right here, this part of it, and you put it into this equation right here, where you took its second and its first derivative and times 3 and times 2, what happened to all of that part of it? What did it add up to?
It was equal to 0.
It equaled 0. So that's why it actually didn't change the check over here, because it's equal to 0. Remember what we just said a second ago? We just said this part of it right here, when you take the second, first derivative, multiply by 3 and by 2, that all by itself, without touching anybody else, without touching any of the rest of this answer over here, that produced the 2t, correct? And then we said, what did this part do right here? After we took its first, second derivative times 3 times 2, that produced the e of t. What did this do? That produced 0. So if I go down here and say 0, this gave us that 0. And so it's kind of cool that there's like a 0 that's, I guess it's always there. You can always say plus 0, and yet that actually produces part of the answer to this. That actually is what creates the entire direction field. That's what's kind of so cool about this. And so, you know, here, when I slide all these around, you can kind of see the direction field for this. You can see all the billions of different answers. And again, wouldn't it be kind of cool to be able to create a direction field for a second order differential? Because I can kind of see it as I slide all this stuff around. And by the way, can you see the asymptotic equation here? Notice it wants to curve down over here, but yet when it's like whipping up in the air and then suddenly boom, now it goes up. It's like somewhere in between those, there's like a transition. Here it goes up, there it goes down, and somewhere in the middle, there's a transition. Again, I just find that interesting. Do you notice where that transition is, by the way, in this particular case?
Looks like it's at 0.
That's exactly right. If you let A and B be equal to 0, isn't that kind of what we discovered on the project? That's the transition. That's like right down the middle. It turns out that in that case, notice this over here, not going up or down. It's actually a line over there. It's just going straight off into space. If I move this just a hair, one way or the other, you know, it kind of doesn't behave that way anymore. It goes up or it goes down. But if they're both 0, that's just kind of interesting. That's all it is. It's just interesting. That's why I thought it was worth playing around with the project. But it helps us kind of understand what the direction field looks like a little bit by noticing that. So yeah, family reunion. Now we're just answering these with, well, I guess you could say all of the answers now instead of just one. And so there's still a family of solutions thanks to, well, what your book calls the superposition principle. I'm not even sure I understand that term, but it's, I think what they mean, I don't know the sort of textbook definition of superposition. I think of superposition as being like, you know, positioning somebody else in place of somebody else, something like that.
I think it kind of like relates to the superposition principle of vectors, because when you add two vectors, you're superimposing them, I'm pretty sure. And so
Yeah.
I think because you're adding two solutions, you're superimposing the solutions. At least that's how I interpreted it, is that generally when there's superposition, it's addition.
Yeah, well, and you know what I showed you a second ago, negative 2/3 t plus 4/9 is the 2t, and the negative 1/4 e to the t is the e to the t, and all this junk is the 0. It's like those are superimposed. You know, this equation up here is superimposed on 0. I mean, I think that's kind of where that language comes from. Anyway, that's pretty powerful. Out of interest, quickly, just from yesterday, notice I went, and I wonder if you could do this yourself in your head really quick, but notice yesterday's huge, ugly differential equation was y double prime minus 5y prime plus 6. Do you see that y, you know, r squared minus 5r plus 6 would be r minus 2, r minus 3. Therefore, the r's would be positive 2 and positive 3. So I added that to yesterday's check. And by the way, what I screwed up yesterday when I checked this is I accidentally put a negative right here. And so the graphs didn't work. They didn't line up. And that after I saw the matrix and went, wow, that pattern is too good. Like, I don't see that there's anything wrong with that. Then I looked at this and went, oh, that's where my mistake is. Change that to a plus sign. Boom, they're the same exact graph. But again, what difference did it make that this graph was on here? It made no difference in the check because that is producing, well, the 0. Yesterday's expression was x squared cosine of 2x plus 0. We just didn't think about the fact that there was a plus 0 on the end of it. So that plus 0 adds these two solutions over here. And so it turns out that this solution isn't fixed anymore. If I turn this off and turn this on, and now I slide A and B around, notice I get just a really cool equation. I mean, that's one of the funnest parts of this section, this thing we're studying, is you just get graphs that are literally the solution to an equation. Isn't that weird? This isn't me just making up some weird equation and saying, I wonder what it looks like. This is literally the solution to a second order differential equation. And so I just get this really neat, if you will, direction field kind of an answer. Notice you can see evidence of two things. You can see evidence of the parabola. Notice that part of it right there kind of has a parabola sort of a look to it. Or you could say, no, I think I see the parabola curving right here. But it also has obvious evidence of cosine. You see it wobbling up and down. But notice the AE to the 2x and BE to the 3x, they play into this as well. But notice they seem to not have much of an effect over there, kind of on the left-hand side. It's like the left-hand side of the graph just seems pretty fixed, but the right-hand side, you know, kind of moves around a little bit. It's just interesting. Beautiful, I think. So the good thing is we actually didn't really have to learn anything, at least hard, new today. So let's try this. let me give you. So the one thing that really needs to stand out to you, I guess, in today is that you really got to look for multiplication versus addition, and you should be sort of happier if you see addition. So let's try this. Let's see, do I make something up? And you saw from yesterday, sine and cosine are dangerous, like for me to include those, because, you know, what are my choices for equations? In this case, I chose a polynomial over here, which was not a terrible choice. Come on, zoom. I chose a polynomial for this. And then I chose an E. That's the two equations I chose to stick in there. Do you understand it's more dangerous to put in sine and cosine? But I was really nice to us because I made the derivatives really easy. So let's try something similar to that. And again, I'm just making this stuff up. So hopefully this won't go off the rails. And then, you know, what can I put on the other side? Well, again, the choices I have, think in terms of the next test. The choices I have is I could write two things multiplied together, or I could write two things added together. But let's do this. Let's make it a, see, a squared term seems sort of dangerous, but let's make it a t plus 5 plus sine of theta. Notice I didn't make it sine of 3 theta or something like that. I'm trying to make the process as simple as possible. I want to know how you should approach this. I want to know what you think. What we learned from above that I would like you to incorporate is the easiest way to do this problem is to do it separately. As it turned out, you know, we did y of 1 up there because we recognized, hey, the 2t is one of our answers. And then we did y2, and that was our other answer. And then we just kind of added them all together at the end. That's actually far easier than kind of collecting them all at the same time. It just makes it messier. And so what I'm saying is, when you see a problem like this, you should be able to say something like, well, there's a polynomial term. Notice I can actually do those together at the same time, because the 5 can be considered to be part of the polynomial. Do you have to do it that way? No, you don't. And then this, of course, is trig. So I'm seeing this as like two problems. I'm going to call this y1 and this y2. But remember, there's a plus 0, so I really should have a y3 as well. So, you know, go get them. Like if you want me to like help you catch your dumb mistakes on your math test, this is a great way to do your work because it makes it really clear. And so I'm going to go get y1, you know, like go get that answer. I want to give you a chance to, like, you got this. You don't need me to show this to you. I'm going to do it, but you do it. Go find y1, choose the right guess. By the way, which one of those should you do first? This is really important. Which one of those three up there should you be doing first?
0.
0. Why, Connor?
So that way you can find out if it meets any of those special criteria right out of the gate.
Exactly. Notice there's a 1 in front of this theta right here. And so if there's an r equals 1 over here, like we run the danger that maybe our guess isn't going to be the right guess. And so it actually is way better to do that one first. I think I made this one up so it doesn't have one of those exceptions. So let's just not worry about that. Just go ahead and do them in order 1, 2, 3. But
So Doug, if out of curiosity, if it did hit that 1 right there, the rule states that don't we also need to have the alpha? And since there's no e in that equation, like we'll never hit that no matter what, as long as there's not an e in this equation.
yeah,
Well, I guess
except
if it's
for
0.
there is right
Yeah,
here
that's
an e to the 0 in front of that. So basically alpha is 0 and theta is 1.
That's gonna get me one day. Someday it's gonna get me.
Yeah, and that's what I mean. Like I could make that happen on the test and make you all fail, right? Which I'm not going to do, but
Not me. I'm gonna
Not
think about it
Connor.
now.
if you didn't think about it, what you would find is what happened yesterday. Like everything cancels out. You're like waiting to try to get A to be 7, except for you end up with like 3A minus 3A equals 7. It's like, oh, the A's all canceled out. Well, that means you made your guess wrong. And then you could go looking and go, oh yeah, that did meet that special case. And you know.
Wait, is that two variables with the t and the theta? Or theta be a constant here?
Oh
we get,
yeah,
like, the
that's not good. No, is that okay? Wait, is that okay? Is that okay that there's a T and a theta? Because I think you're right. I don't think that's okay. That should be a T. Yeah, we don't want two different variables. It's theta that's 0. I'm sorry, it's theta that's 1 here. Theta would be 1 because it's sine of 1t. Thank you, Ben. That was a mistake on my part.
It's kind of weird though, because like, yeah, in these formulas, they treat theta as like as a constant, but normally it's a variable. We're used to that.
Exactly. That's exactly right. So yeah, in this problem, you would actually say theta is 1 and e to the 0. So alpha is 0. To me, this is a pretty good example of a test question because this isn't going to take terribly long to answer. Work on your work. Is your work for Y1 as clear as mine is? If your work looks like that, I'm going to totally be able to diagnose what's wrong with it. Waste a little paper. Box a few things, make it really obvious. If you don't put a box around something or, something to highlight it, a few of you actually use a highlighter. Connor uses a highlighter on stuff. It's like that really helps somebody else, help you. So I just did Y1. There's a bunch of work for that. Now I think I have the answer. I'm going to go get Y2. Y2 as a guess. What's your guess for this? You got to be really careful. What's your guess for sine? Notice it's not sine times anything. Do you know what the correct guess is for this? Can you look at the note sheet and get the correct guess? And the note sheet is a little bit too broad, if you will. It's like covers lots of circumstances. If you're struggling with this at all, take a look at the note sheet. What does it say if you have a sine? Notice this is what I have. I have this equals sine. For me, theta is equal to 1. And this isn't here, which means this isn't here. This isn't here, which means this isn't here. So it's sine plus cosine. Now, having said that, I did cover up something that really shouldn't have been covered up,
Don't you need a coefficient?
and that is this. Notice what is sitting in front of our sine? T to the 0. T to the 0 is sitting in front of that. That's 1. In other words, so this is t to the 0 power right there. Well, notice there's still a g there. There is constants in front of that. So assuming I didn't, assuming I don't accidentally get into that mess, the exception to the rule thing, your guess for this should be a sine of theta. In other words, an exact match. Ours was sine of, not theta, t. But there also needs to be a cosine, even though you might think, why would I need that? But remember, we're taking derivatives, and the derivative of sine is cosine, and the derivative of cosine is sine. And so we need both. That's what that note sheet is saying. If you just guessed a sine of t, you're not going to get it to work. And, is it okay to reuse a? I used a up above, you might think, I don't want to reuse a. Well, good. I think that makes sense. Column C1, C2, C3, C4, just so it helps you remember their constants. That's all fine. Those are good. And I did write an answer down wrong. And I wrote y1 down as 1/2 a, but a was 1/2 the t. The t is the thing that goes there, not the a. I didn't notice I did that dumb thing. So the point is, in y1, the a has already been used up, and so is the b. I don't see them anymore. Their work is done. So it's okay to reuse them. So then, of course, in order to plug things in, you're going to need the first and second derivative. Derivative of sine is cosine. The derivative of cosine is negative sine. And because I was nice and there was no coefficient in front of the t, we don't have to do the chain rule. So the third derivative, the second derivative of y2, then the derivative of cosine would be negative sine. And the derivative of sine is cosine. And so I'd have all that junk. And as I have illustrated, it's really easy just to write down tiny things incorrectly. So now I just plug all that stuff in. So that means negative a sine of t minus b cosine of t. There's my y double prime plus 3 y prime. So that'd be 3a cosine of t plus minus 3b sine of t. There's my minus 3y prime plus 3y prime. And then a plus 2y. Plus 2a sine of t plus 2b cosine of t. There's my plus 2y. And I need that whole thing to equal the sine of t. So that means all my sine statements have to add up to 1, since that's a 1 sine t, but then all my cosines have to add up to nothing, because that's nothing cosine. Does that make sense? So let's see, to get sine, I have a negative a sine, and then I have a minus 3b sine, and then I have a plus 2a sine, and so that all has to be 1. And if you were doing this so that somebody could understand it, you know, maybe you say this is, maybe you make a note, this is your sine of t equation or something like that. And then my cosine equation, I have a negative b cosine, and then I have a 3a cosine, and then I have a 2b cosine, and that all has to be 0 because that is my cosine t equation. Notice the pattern again. See the pattern in the coefficients? 1, 3, 2, 1, 3, 2. All the signs. It's interesting. So this isn't hard. I just have 2 equations, 2 unknowns. So in all total, I end up with a minus 3b equals 1, since I can put the a's together for the sine equation, and I can put the b's together for the sine, for the cosine equation. And again, notice the pattern to that. There's a 1 and a 3 and a 1 and a 3. Just kind of helps me know that I didn't do anything wrong. This feels like more trouble to stick into the matrix to me than it does just to do it in my head. So I'm going to take the approach of multiplying this one through by 3 so that I can add the b's together. If I do that, I get a plus 9a was 10a. I get no b's, and I get 1. So I think a is 1/10. I'm going to check my work. If a is 1/10, then let's see, looks like the bottom one would be easier. So I'd have 3/10 plus b equals 0. So that means b is negative 3/10, I think. So then I go back to my guess, which was clear back up here. In other words, I knew the answer looked like that, and now I think I know what a and b are. For a second there, I was like, wait a second, what did I just do? What did I just found a and b, like, what are those again? I don't even know what I just did. It's like, well, that was a whole page ago. No wonder I don't know. So I think y2 is equal to 1/10 sine of t minus 3/10 cosine of t, but I'm very shaky. Like, there's just so many things I could have done wrong there. One of the things I'm going to do really quick just to check is I'm going to put those in. I'm going to erase this, but I'm going to just put those in right here. Make sure I didn't do something wrong. If I put in a is 1/10 and b is negative 3/10, is that actually true? 1/10 minus 3 times negative 3/10. Yeah, that's 1/10 plus 9/10. That is 1. Or down here, if I put 1/10 here and negative 3/10 there, that's 3/10 minus 3/10 is 0. So now I'm thinking I didn't get that wrong. I think that was worth my time to double check that. If I was taking a test, I might just stick that in the matrix. After class, if you haven't been shown how to do that, 1, negative 3, 1, 3, 1, 0. If you haven't been shown how to just stick that in the calculator and use the RREF, reduced to echelon form, RREF means something to people that took 261. It means nothing to you if you've never taken that class. And then finally, the homogeneous case. The auxiliary equation for this, where this started right there, was 1, 3, 2. So 1, 3, 2. And again, that is coming from the fact that we believe the answer to this is equal to y equals e to the RT. And so I'm about to find out what those are. Well, this one, if I put it in the quadratic formula or factor it, factors to r plus 1, r plus 2. So that means r is equal to -1 and -2. And so my Y3 answer is C1e to the -t plus C2e to the -2t. And so there's what I think is my answer. I think that's my third and final equation. And notice, just to kind of go back and double check, when we played with this at the start, notice we had e to the 0. And in order to be a match, we would have just had to have found an e to the 0, but we didn't. We found e to the -1 and e to the -2. And so, whew, you know, good deal. This wasn't one of those special cases. How do we also know it wasn't a special case? Because nothing canceled out. Like, it worked, which I found answers to everything. That wouldn't have happened. If we made the wrong guess, then it wouldn't have worked. But it did work. So all that remains then is just to kind of write all your answers together. Now we think we now have the, what you would call the general solution to this. And all, of course, I'm going to do is just go add all these things together. Just write them all down in the same spot. I am going to copy them. So I'm just going to add all of those together and I'm done. Guess I don't really need all of that, so. So this was a plus sign. And then I've just got that last part to add on, which I think I'll just leave again the same exact color. And you get answers to these that are, you know, so long you can't not really see the entire answer, but there is the general solution. I found the solution to the second order non-homogeneous. Although we just discovered today, all of them are homogeneous.
It's funny that this is still Y general. Is it Y general because we don't know C1 and C2 still?
Correct. That's why it's general. Now, just to watch this work, I get the idea that this is not going to be terrible. Do you agree with this statement? If I was to go back and make up some initial conditions, is this a terrible idea? I actually really don't know. Is this the kind of thing I should not ask on a test because this is going to be a hornet's nest? They won't ask this in the book and because it's, you know, pretty long and this could take 10 minutes and so forth. Do you think this is a bad idea for me to say y of 0 equals 2 and y prime of 0 equals -1? Is that going to cost us a bunch of time? Is that worth?
And then we're going to solve for the constants.
Yeah, in order to get the constants, I'd like you to see this working, I guess, is what I'm after here. Because I made up a fairly simple equation, I don't think this is going to be terrible. So let's go. Let's try it. Maybe we'll.
Yeah,
maybe I'll
it's hard to
change my
say.
mind.
The constants should be 0 though, right?
No, they're not 0. C1 and C2 are not 0. Now they're going to be something. So I'm going to start with that one. Well, if y of 0 is 2, then that means the y is equal to 2. But notice it's really nice that I said y of 0 is 2. Does it make sense if I said y of, say, 1 is 2? That would have been more of a bummer. But since t is 0, notice there's not a lot of stuff that survives. Sine of 0 is 0. So 1/10 sine, that does nothing. Cosine of 0, however, is 1. So do you agree that that makes a contribution? So the 1/2 t was gone, but the 7/4 survived t being 0. Sine of 0 is 0, so 1/10 sine of t was gone, but cosine of 0 is 1, so -3/10 survived. And then what about the rest of this? Well, again, 0 is really nice. C1e to the 0 is just C1. C2e to the 0 is just C2. And so there's my equation. Now, I'm going to take 2 and subtract 7/4 on my calculator because I don't trust myself. And I'm going to add 3/10. I'm looking at my calculator to make sure they're actually all typed in. And I got 0.55 for that, which is actually 11/20. So I got C1 plus C2 equals 11/20. And I made this up. So of course I got, some kind of a weird answer. And so like, there's my first equation. And I can't solve that because there's thousands of answers. And basically that's what I showed you on the graph a second ago. There are thousands of graphs that go through the 0.02. That does not help. But what if we move on now and consider our second? Remember, this is the one that said I pulled the kid back 2 meters and then I let him go. But then what does this mean? If you pulled the kid back 2 meters and then -1, what did you do to the kid on the swing? You didn't just let him go. What did you do?
You like tossed him up more.
You pushed him in the opposite direction you just pulled him.
Oh, gotcha.
Because 2, whatever direction you're calling positive, was one way. So this is like you pulled the kid back, but then you pushed him forward. Does that make sense? And so you pulled him back to 2 meters and then you pushed him away from you at 1 meter per second. That's why these conditions are so cool. Why is this one a bit of a bummer though? Why is this particular one a bit of a bummer? Well, it means I got to take the derivative of the dumb thing in order to use it, right? Before I just was able to stare up at my y of g equation, but now I've got to take its derivative. But fortunately, taking its derivative is going to get rid of some stuff, right? 1/2 t becomes 1/2. 7/2 is gone. 1/10 sine of t turns into 1/10 cosine of t. Derivative of cosine is negative sine, so that actually turns then into positive 3/10 sine of t. And then notice the e's. The derivative of e to the negative t is e to the negative t, but when you multiply by -1, that turns into a minus c1 and a minus 2c2. And so now I start plugging stuff in and I say, okay, y prime is equal to -1 as long as t is 0. Well, the 1/2 survived that. Cosine of 0 is 1, so the 1/10 survived that. But the sine of 0 is 0, so that's gone. And then you end up with a minus c1 and a minus 2c2 because e to the 0 is 0. Do you agree with that? Like there's our second equation. So again, I find myself wanting to Go ahead. We're good?
I was just saying it looks good.
Sweet. So let's see, I'm going to add C1 and C2 to the other side. So I have C1 and C2 over there. And then I have 1/2 plus 1/10 on the right side. And then I'd have to add 1 to get over on the right side for a total of 1.6, which is 1 3/5, which is 8/5. So there's, if you will, my second equation, except for there's a 2 in front of that C2, I realize. Hopefully I didn't do anything dumb there. So this time, just because I'm sort of feeling lazy for some reason, I am going to put this all into the matrix. 1, 1, 11/20, 1, 2, 8/5. And notice the matrix feature does not work unless these are lined up. In other words, I have C1 first, I have C1 first, I have C2, and then I have C2, and then I have an equal sign. You have to have an equal sign with the number on the other side, And so that's what I'm going to stick into the matrix. I go second matrix, I go over to edit. I say I need a 2x3 matrix. I put in 1 and then 1 and then 11/20. It's so fast. And then 1 and then 2 and then 8/5. So fast. Second quit, second matrix, go to math, reduce to row echelon form. Matrix A, boom, gives me my answers. I turn them into fractions. And this tells me that C1 is equal to -1/2 and C2 is equal to 21/20. Again, a lot of room for mistakes. But I now have what I would consider to be a particular solution. And if it wasn't for the ability to copy, I would not be writing this particular solution down. But since I can copy all this, I think I will write it down. Y particular, get rid of those guys. Find a new color to highlight the fact that I'm plugging this in. I found C was -1/2. I found that C2 was 21/20. I mean, I've been doing this problem for like 20 minutes, right? And I'm really good at this. I've been going fast. I probably passed you up, right? I passed you up doing this because I'm really good at algebra and I'm obviously know what it is I'm teaching you. But as I've been saying, for me personally, the chances I got this right are really slim because I just am probably going to make a math mistake. So what I'm going to do this time, though, is I'm going to check this by just typing that particular solution in, and I'm going to look for those two initial conditions, and I'm going to see if I met those. That's kind of a cool way to check it, isn't it? Just going to type that whole mess in. So I'm going to go back over to Desmos. Type this in. I got 1/2. Let's say 0.1 instead of 1/10. Taking too long. 0.1 and then minus 0.3 cosine of t. Then I figured out -1/2, I think, e raised to the -t power, and then plus 21/20. Let's see, that would be 1.05, I believe, plus 1.5 e raised to the -2t. And I'm going to stare at that and see if I typed it in right.
That's a crazy looking graph.
Isn't that fun? Such a fun graph. We'll talk about that in just a second, but if I zoom right here, do you see the good news? Why is there good news there? What do you see? Like, yeah, baby. What do you see it? Of course, y of 0 is supposed to be 2. That's a good sign. But can you also see the slope? Y prime of 0 was supposed to be -1. Do you agree that right there, the slope really does look like -1? So I'm feeling pretty good now. So as I said before, this is just kind of fun, but I go back here, and before I determined what these constants were, and I thought they were C1 and C2, I'll call them A and B here. Remember, our solution was just one of a family of solutions. Notice they all seem to kind of have this exiting the stage right. It's almost like a sine wave that's climbing up a hill, if you will. Notice it seems to not have any effect on that. So that's kind of interesting, you know, like why is it doing that? That's awful fun. I mean, that's kind of a fun family of solutions. It's really beautiful, beautiful kind of a graph. Really happy to see that, if you will. Let's see, just since we can, let's check this the other way too. See if I can get this to be stuck in your head. What was the original equation? Plus plus 3 plus 2, wasn't it? It's plus 3 plus 2. The whole thing was supposed to be equal to, for some reason I can't remember that at all. T plus 5 plus sine of t. That's what it was supposed to be equal to. So
I
if I
could give
turn
an
this
extra
off,
T in there.
t plus, no, that's good. Wasn't it
never
t
mind.
plus 5 sine of t?
Yeah, actually, yeah.
Right. Was the original equation plus 3. Yeah, that's right. So what the heck is all that blue action? It's kind of like they're the same over here, right? It's the same over here, but it's not over there.
For some reason, I think this is the coolest graph we've ever seen.
It is pretty cool,
I
isn't it?
don't know why, I
This
just
is-
like it.
Yeah.
I think in order for these to be exactly the same, don't I have to go back and no, because it was supposed to work for any A, B, right? Without initial conditions. So this is right. So I'm a little, just to be, honest with you, I'm a little concerned. It's like, how come the blue graph, the green graph, it's like they match up, but then they sort of don't match up when T is like the big negative number, like they stop matching up.
I
But
thought
notice
you were
it's
about to be disappointed. I was about to be sad.
Well, does A and B up above those equations do anything to the equation below it?
yeah, it's like it doesn't seem to affect the, it makes
What if
sense.
they're
It's
both at
affecting the
0?
blue equation. Yeah, what if they're both at 0? That's a pretty interesting question.
There you go.
Whoa. There we go.
Not surprising in a sense that they're exactly the same graph. Remember we said that, that this is t plus 5 plus sine of t plus 0, right? Isn't that what it really is? And so we said that's part of the solution. But if I took those off, which is really what I just did by making A and B 0, right? I just took them off. Notice it's an exact match. And so let's reason this out together. How come if those aren't 0, it's kind of like they're the same graph, but they're kind of not, right? Or they're the same out to the right, but it's, what's that causing? That's bugging me. I just expected them to be the same. That's what happened a minute ago. Remember, it made no difference. They were the exact same graph. That's what I was expecting to see, but it's kind of like they're the same graph, but they're kind of not. Like when t is the wrong number, when t is a big negative number, then it kind of freaks out somehow.
Out of curiosity, if you go to like -5, like up where we think it's perfectly in line on the graph, is it perfectly in line, or is it still kind of oscillating back and forth across the line if you go really in?
Yeah, that's a good question.
Well, it looks like it's perfectly on it.
Yeah, it does, doesn't it? If it's not, I certainly can't seem to see it.
Yeah, it would have been pretty cool if it was oscillating still.
Yeah, microscopically. And that's what Calc 3 is about, is, microscopic oscillation. So interesting.
So that was kind of my question earlier when I was like, so A and B are supposed to be 0, because it seems like every time we throw it in the graph and A and B aren't 0, the graph doesn't match.
Let's see what happened over here. This is the ridiculous one we did at the end of class. That's interesting. I never noticed that before, but it does have the same type of behavior. Like it is an exact match here. And notice A and B are weird things.
I don't think we could see your screen.
Oh, you can't see that. I'm sorry. Thank you. Got to reshare. So this is that ridiculous one that was 6 equations, 6 unknowns at the end of the day. Notice if I, again, look in here, they're the same exact graph. But again, outside of a certain range, it seems to kind of go off the rails. I don't have an answer to that, honestly.
That's so weird. I wonder if it's Desmos messing it up and it's not actually like that.
Yeah, that's possible. And it's weird that it's like one-sided. It seems to, like in this case, it seems to be fine over where t is negative. And then when you get above t is, 12 or 13, then all of a sudden it kind of starts wobbling and goes off the rails. Whereas the other time it was over on the negative side. And so, what's causing that? Honestly, it seems like the answer to that is not that hard, but for some reason it isn't jumping
Yeah.
out at me.
Something to do with like how Desmos takes derivatives, like it messes it up somehow. I don't know.
That's a good question. Yeah. Like it might be, remember Euler's method? And so like when I say derivative, it's not like, I bet you that actually is the answer. Desmos is not taking the derivative, actually. You and I know how to take a derivative, product rule and all that stuff. It doesn't know how to do that. So it's doing it using Euler's method where it just takes a small number, but if it's approximating it, then it's going to go off the rails. And so I actually have a feeling that is exactly the reason. These actually are the same graph, but we just aren't able to see that. So we can see it okay as long as we're, inside a fairly small range.
So basically the C1 and C2 values we got, if we plug them into this particular answer, it should still match the graph perfectly, right?
Yeah.
Okay.
And again, that's because those values right there are producing the 0 over here.
So it matches the graph perfectly when we solve for it, and it also matches the graph perfectly at 0. Just trying to wrap my brain around this a little bit.
I'm not, is it gonna? Yeah, this. Yeah, so it's like when you put 0 in, then it was okay. So in a sense, it's kind of like, yeah, it's that's causing it, I guess. But I have a feeling it's because, it's taking a derivative of e to the 3x, which it's not able to do. It does not know the derivative of e to the 3x is 3e to the 3x. It's not doing it that way. And exponential equations, get really big really fast. And so kind of makes sense that that'd be the case, I think. Again, it's kind of fun to look at this graph because notice it's a combination of a parabola and a cosine. And so you can see the cosine wave. It's just that the cosine wave starts to kind of wobble out of control really fast, which again is the Tacoma-Narrows bridge failing. It starts to wobble and it keeps wobbling higher and higher until you just can't structurally support that wobbling anymore. So let's do just a couple other quick questions then. Took us like 2 pages to do that problem. So that wasn't terrible. Like on a test, if I was sort of careful about it, that's kind of cool to produce C1 and C2. I'm certainly going to ask you to do that some places on the test. Maybe it's less appropriate here because it's kind of so much work, but I always make a key for my test before I give it to you just to make sure it is reasonable in terms of the amount of work and the time and what happens and so forth. Let's see.
The farther I go in math, the happier I am with my investment in like a tablet, like an e-tablet, because I'd be killing so many trees with these problems.
No kidding.
I've been running out of paper, so I've been tempted to get a stick and go outside in the dirt.
There you go. I
Go
firmly
find
believe that's how
find an
Newton and all
acre.
those guys learn this stuff, man. But something about stick and dirt is just magical.
Instead of man versus wild, it's man versus math.
That's right. And the rocks are our calculators.
So let's not do this completely because I honestly don't really, there's nothing like another example of this. I'm not sure is going to make a lot of difference, but I'm just going to throw one question there and let's try to at least write down the proper guesses for this. And maybe let me do one more thing before you kind of bust loose on this. Let me write this like in red. Would you agree? This is one of the equations. This is another one. This is another one. So let's call this one y1 because you should always do the homogeneous one first in case there's a problem, in case there's a special case. And let's call this y2 and this y3. And so we're going to have to find 3 separate equations. But notice y3 is actually one of those multiplication problems, right? So it's like, so all I want you to do is write down the proper, like actually answer y1, but write down the proper guess for y2 and y3. So actually solve y1, but just y2 and y3. Create the guess, that's all. I'll give you a slight hint. Be a little careful here.
Was that the hint?
That's the hint. Pretty big, huh?
I was waiting for it.
Here's a hint.
Where-
Don't matter.
Wait, be careful.
Hint
Where that's
is,
I wasn't
I'm
looking.
gonna give you a hint. That's the hint.
Oh, thanks. That's got it now.
I'm gonna be triple guessing every move I make.
That's what
Wait,
that's all I'm after. That's all I'm after is like, be
Did
careful.
you circle Y1 when you said be careful? Be careful where?
There's a reason I had you do y1 first.
Oh. Oh
See?
shoot. Okay. I found
So
it.
you guys just charmed it out of me. Like I didn't want to say that, and now you just charmed it out of me.
What else can we charm out of you, Doug? Maybe some answers to the test.
Yeah, I'm pretty easy.
You know, when I was in high school, I had a chemistry teacher, and every time we'd have like a question about like like the wording of a problem on the test, she'd just tell you how to do it.
Yeah, you're like, can you explain what you mean by number 2? That's awesome. We had a teacher who's like, tell us about when you used to play baseball for the Dodgers. And I was like, and then the whole class would be over and we wouldn't have any homework. Same thing.
Funny.
So did you get the homogeneous answer? Y1 equals C1e to the 2t plus C2e to the 5t.
Thus far, the part I screw up the most is the finding the roots.
It feels like so long ago. I don't know why.
I always get hasty and write down the I'll see like r minus 5 and be like, oh, r is equal to minus 5.
Right.
Yeah. I'll get the R's and then I'm like, wait, what do I do with these again? And I'm like, oh wait, I just put C1 and C2, and it's like it seems too simple. It's almost confusing.
Oh yeah, it totally does.
Yeah, in a sense with the homogeneous case, it's actually kind of better to start out and say, we're going to guess the answer is e to the something t. And then you write down the homogeneous answer so you understand what you just found. Like, what is R again? What did I just do?
Yeah, it's getting to the point where I've made enough dumb mistakes on math tests that I'm like, I'm gonna have to just start writing everything, you know what I mean? Just to like keep my thoughts straight.
So for the trig expression, what's your guess for that? Since it's cosine of 4t. Do you understand that it's going to need a cosine of 4t and a sine of 4t? And that those need some kind of a coefficient in front of them? You understand that'd be your guess? Again, unless there's a curveball or something like that's your basic guess for that. Again, we're very happy there was not something in front of that cosine. But Y3 is the curveball. Do you see it? Notice it's multiplied. And so your knee-jerk reaction guess for this should be, oh, it's a polynomial, which requires the highest degree possible, which for us is t to the 1, and then all the constants underneath. And so it's going to need an at plus b because of that t. And then, of course, it'll just need whatever the e is. Like that would be your guess, except for that's not going to work this time. Do you see why?
Because it's a root. 2 is a root. So
Yeah.
is 1.
There's a match. In other words, in our y1, we already had an e to the 2t. And so if you tried this, stuff would cancel and you'd get no answer. Like if you didn't notice this, and after class, you might try that, like convince yourself that that's true. Like if you didn't notice it. And again, I think, you know, certainly 3 weeks after this class is over, you know, if you were lucky enough to even just look at the note sheet and write this down, this is a good guess. But the question is just, you know, if it didn't work, would you kind of go, oh, maybe that's one of those special cases, and then re-guess? Now, what's the guess that would work then, given that that's a match? Stare at the note sheet for a second. So we are looking at this case right here.
We
Are you
throw
able
a
to-
T in the front there.
Yeah, so notice we have, that's exactly right. Notice we have an e to the RT, but then it says if R is a root of the auxiliary equation, our R was 2. Is that one of the roots? Well, yes, it was. Oh no, what's that? What's the case then? Then you let S be 1. S, what the heck is S? S is that right there. In other words, take your polynomial and multiply it by t to the 1. If it wasn't a root, then no problem. You just like ignore it, and that would have been great. But because it was, then you need to multiply your whole thing by t. That's what this is saying. So that actually would not work. Go do this after class and just notice that stuff will cancel out, as I said. And so your actual guess is not that. Your actual guess in this case should have been multiply everything through by t. And then it'll be okay. And again, you should agree, I had to like think to make that question up, didn't I? You have to try to make that happen. That's not going to happen accidentally. I'm going to erase this, but who can tell me this? When would this have to be the guess?
A double root.
A double root that also matched. So since it was 2 for us, then I guess the original auxiliary equation would have to have been to be y minus 2, y minus 2. Wouldn't it have to be this? Wouldn't that factor to r minus 2, r minus 2? And so not only is it 2, it's a double 2. And then that would have had to, the green would have had to have been our guess then. And so just interesting.
It's nice that if you notice this after the fact, all it takes is just like adding a t onto the outside of the parentheses.
Yeah. Yeah, you wouldn't actually have to do all your work over again. You just, it alerts. It's not like you get the problem wrong and don't know it. That's the thing that's kind of cool. It's that it cancels out and you won't find an A and B that actually produce the answer. Like, oh, I can't do it. You know, and that's kind of a hint like, oh, something's not right. And you're
Yeah,
right. You can just go back to your work and, you know, add a squared and a t there and sort of just erase a few things. And, you know, so you could actually survive this.
Yeah, unless you're like second page deep in a trig problem, then you're like, over.
Exactly. But that's kind of cool because, you know, we're pretty far out in the universe here, aren't we? Like, look at that original problem. We're a long way out in the universe. Not only are we solving a differential equation, this is a second order differential equation. Not only does it have a derivative, it has 2 derivatives in it. And then it isn't equal to 0. It's equal to, well, everything you've ever seen. E and t and cosine. And now I don't know the answer to this off the top of my head, but how come there's no logarithm? Like, why isn't that one of them? How come there's, like, I'm thinking of all the equations I know exist, and I think polynomials, trig, and exponentials, and logarithms. Like, is there some reason? Let's just, I truly don't know. I'm trying to decide if I should ask this as an extra credit question, but why is it never, you know, this? I usually take the time to make these up to factor, but this time I'm not. But why is it this, like, how come that's never a thing? I wonder if it's like not possible. Is there like no way to do it somehow?
I bet you could do it with like hyperbolic sine or cosine, since there's e to the x's and stuff involved with that. Probably solve something with that.
You very well may be right. Why is it immediately? Why is what has worked really well with polynomials and trig and e that does not work really well with natural log?
it's easily differentiable. Like the derivative yields an answer that's kind of compatible with the, I get, what's on the right side of the equation.
Like, and here's another thing we never saw. Like, how come it was always sine and cosine? Like, why wasn't tangent? It relates to what David just said. Like,
Because this derivative is secant, and it's kind of tough to get rid of that with a second derivative. Oh, with only a second derivative.
yeah, I mean, think about a polynomial. When you take the derivative of a polynomial, don't you just get a simpler polynomial? And when you take the derivative of sine, don't you just get cosine? And then you get your sine back again. When you take the derivative of e, you get e. But when you take the derivative of tangent, you get secant squared. And when you take the derivative of secant squared, like you see how it just goes off the rails? Does it make sense if I was to take a first and second derivative of tangent and try to add it together? Like, it's not going to come back on itself. Does that make sense? First and second derivatives of tangent are really messy. And logarithm, the derivative of natural log is 1 over x. And so it's like, what would I be guessing?
We never saw any like functions with a negative exponent either. At least I can't remember any.
Yeah, like what about t to the negative 2 power? Like our polynomials were always positive, but it's like, and you brought up the question, I think yesterday, David, could it be like t to the 3 halves? So, does that go off the rails? But at the very least, I don't want to go down this road, but it's like, at very least you can see maybe this isn't possible for certain functions. Maybe you can't even do it. Or if you can, maybe it's like, you got to learn more. Like, it's kind of like, I can hike Table Rock. Like if you can walk, you can hike Table Rock, but it's like, you want to go hike Mount Hood. Okay, well, we better get some ice axes and crampons. And like, we got to get a little more serious about this. So maybe, maybe that's what's going on here. So, of course, again, this is what, if you're a true mathematician, you're like, oh, I'm suddenly curious. And now you want to go try that. And, maybe later down the road or something like that. If you're not a, kind of more of a practical mathematician, you're like, well, give me a reason to do that and then I'll do it. I'm curious about it a little bit. I mean, like, would it be possible somehow to come up with a function that would produce natural log? But again, I think, man, no matter what I pick, it's going to have to produce a natural log. You know what I mean? Like, well, you might remember the integral. I doubt you do, but you might remember the integral of the natural log of x is x natural log of x minus x or something like that. It's either x natural log of x minus x or x natural log of x plus x. I can't remember. So, but unfortunately, the derivative of natural log is 1 over x. And so does it make sense if you pick this to be your guess? That's not going to work, because what's the derivative of natural log? It's 1 over t. So y prime would be a times 1 over t. Well, good luck adding that together and getting it to produce natural log then. Does that make sense? You have to have something that you take the derivative of, and when you do that, you get natural log. Otherwise, there's no way to add it up and get it to be natural log. So I just think that's interesting to stop and think about. So again, you just understand, like as a math student, we sort of feel like, hey, I'm solving all of the differential equations that exist in the world. No, you're actually being given ones that are really carefully defined so to make sure they work, right?
That would be discouraging if there were not for the spring example. At least there's one case where if you're concerned with vibrations, you can be utilized.
Yeah. And I can't wait to get into that. And by the way, that's effectively next week. So you may notice, because we only have so much time, you may notice next week there's a project and then there's free mechanical vibrations, which is 4.9. We just did 4.5. We're skipping 4.6, 4.7, 4.8. We're doing 4.9 free mechanical vibrations and then 4.10 forced mechanical vibrations. We're going to basically be applying this to a spring. Like I'm going to give you the equation for the spring, which by the way is already on this sheet right here.
Wait, is there 2 projects next week? One
Yes.
on Monday, one on Thursday. Wow.
Yeah, really the Thursday one is for like over the weekend.
Cool.
So, we're going to be looking at this spring equation, which I actually made for you at the start of when I started explaining this. We made this a little bit, but we're going to play around with all of that next week a little bit. I also want to just quickly, actually, there's 2 things I want to do. I want to quickly show you that project right now, just because I want you to begin thinking about it, because this is for me, as a person that draws house plans, this is the coolest thing ever. So I'm more excited about this than you are, if you will. However, having said that, this is one of the places in the real world where you understand that, man, this is important. So just to introduce it a little bit, just to get you thinking about it. And when I show you this, like, don't go try to do it, because I've got to show you a lot of stuff. I'm going to almost be teaching the entire period just to help you even understand this question. But can you appreciate that if you have a beam that is supported over here and it's supported over here, that the beam is going to bend down in the middle a little bit? It's going to bend down in the middle a little bit. And in the world of, you know, bridges and buildings, and I mean, there is beams everywhere. I mean, these things are ubiquitous in our culture. Ubiquitous means everywhere. If you have a window in your house, glass cannot support your roof. So over the top of that window, there's a big beam up there. So every house has got 50 of these in it, and really nice houses have 100. And of course, like I said, bridges and so forth. There's just, so does it make sense that knowing based on the size of the beam and how much weight you're going to put on it, you need to be able to predict ahead of time how much it's going to bend down? That's really important mathematically. And there's a super easy algebra equation to do that. And I said algebra, like, it's really easy. You could teach it to a first term algebra student. You could just say, hey, here's this cool equation that models how beams work. And I'll introduce that to you, and I'll show that to you next week. But it's actually differential equations. The only way to create a model for this is to have a differential equation in it. And there it is. E times I, notice second derivative of y with respect to x. You don't understand what that means right now, but notice it's got, if you want to talk about it, you got to talk about it by getting a second derivative involved. And again, it has to do with exactly how I introduce springs. Force is mass times acceleration, and acceleration is the second derivative. It's the change of position. And so in order to come up with a model of this, mathematicians were the ones, if you will, that were sort of smart enough to figure out this. And so they were able to write a differential equation, which happened to be a second order differential equation. And then they were able to solve it, which, notice now you're thinking, hey, I can solve second order differential equations. That's why the project was here. And then that second order differential equation just produced a normal equation. Isn't that what we've been doing? We've been taking really ugly looking equations and we've been producing ordinary equations from them. And in this case, though, the ordinary equation is actually going to tell you how much this thing's going to bend down. In this case, x is how far away from the support of the beam you are. There's an x right there. Notice it's dy dx. X and then y is how far did it bend down. And so those are, that relationship between how far am I away from the support and how much does it bend down is the backbone of what I do when I'm drawing house plans. I mean, it's nice to say, hey, let's have a bedroom over here. But, you know, if I can't make the house stand up, that's going to be really significant. And so it's like, this is what I do when I'm drawing house plans. And so this is just really cool. So I want to, again, give you a whole bunch of help to, as I said here, develop the equation for that elastic curve. Notice that curve right there. What do you think that curve is? You got a whole bunch of choices because you know a lot of algebra. What kind of curves are there in the world? You tell me a couple of them. That curve B, what shape is it?
Well, I mean, there's a bunch of different curves. Like, it's kind of parabolic, but I don't think it's
Be a
parabola.
parabola. Yep,
It is a parabola?
it could be. I'm not going to answer yet, but
Oh.
we could be a parabola, right? What else could it be?
I took an engineering class. We talked about satellite dishes, and I can't remember if I think that might have been the same curve.
Yeah, curves. Satellite dishes are parabolas. So that could be a parabola. What else could it be?
It'd be a hyperbola.
Could be a hyperbola. That's a weirder one. That was one of the conic sections. Could be an ellipse.
Yeah.
Could be a circle. And we have equations for those things, or perhaps it's like some curve we don't know yet. You know what I mean? But it's like, that's what we need. We need the equation for that curve. If that was a parabola, y equals something x squared, then we'd be able to use that equation to figure out, you know, what that distance is. But we got to come up with the equation for that curve. Does that make sense? Because then we'll own the relationship. between distance and depth that it bends down and so forth. And so,
Like I've seen a problem like this having to do with like the calculus of variations before, but like which is what you use to solve like the brachistochrone problem. So I don't know, I feel like I've seen something semi-similar, and I feel like it was a curve I'd never seen before. So I don't know.
yeah. And by the way, notice it doesn't, it could be a parabola, but couldn't it all be also be a cubed equation? Like, don't cubed equations have curves in them too? Sort of feels like, it won't be cubed, right? But actually, I mean, all the polynomials, cubed, 4th degree, 5th degree, 6th degree, could actually be any of those, couldn't it? Well, that's what we're going to discover. That's what we're going to play around with. And again, I want to give you a ton of help with this because this is, it's a challenging question. I want you to work with other people. And by the way, like on this last project, when I say work with other people, I mean, you turn in one page with 2 people's names on it. Like, you don't have to turn in 2 separate pages. Maybe you talk about it and then you write yours up and they write theirs up. No, turn in one paper with like 3 names on it. Like, I'll just discuss it and one person volunteers to write it up and the other 2, buy them coffee for that extra effort or whatever. But I really want you to work with other people on this because I want you to get it. It's just neat. It's neat for me personally. When I draw house plans, it's really neat that I actually understand this deeply enough that I can talk with anybody, because although we already have the algebra equation, mathematicians have already made it. But we're going to make this tool for ourselves, if you will. But just the ability to understand it that deeply is the kind of thing that gets me jobs. Because if I'm talking to somebody and they have questions about things, like I get it far deeper. I know answers to questions they probably aren't going to ask me. And this is an example of one of those. But that allows me to engender confidence in them because, they're going to hand me $5,000 to draw them a house plan and they'd like to know I know what I'm doing. And so that confidence that you can put in them because you actually know what you're talking about is important. And sometimes it's not enough just to say, oh, I have a degree. I took this class. But to be able to converse about it, I just think it's kind of cool. Do I need it? Absolutely not. I actually don't. I don't need to know this actually for anything in terms of what I do, because I've shown you that beam design program that I use, but it's just interesting. Anyway, so that's already posted. We're going to start playing with that on Monday. One other thing I just want your advice on really quick. So I'm actually flying. I have to do a wedding for somebody on Saturday. I'm flying out early Sunday morning, and I'm going to be in Idaho where my kids are Monday, Tuesday, Wednesday. Fine. You won't notice a difference because I'm just going to teach you from Idaho Monday and Tuesday. But unfortunately, the only flight I could get flies out at 7:30 Wednesday, which means I'm going to be up in the sky if I'm lucky. If I'm on the ground at 8 when class starts, that means I'm dead. What should we do Wednesday? That's my question. I could make the lecture between now and then for Wednesday. And then you could just watch it like at your convenience, which maybe you're doing anyway, since I'm posting lectures right after class anyway. So that's an option.